Part 7, angular momentum. So this is kind of the crowning jewel of this whole exercise, this whole process. What we're going to show is the elliptical orbits that planetary bodies have around the sun. So it seems like such an obscure thing to show, but we're gonna do it in this video, and I'm hoping I can get it in one video. So the title of this video is called Angular Momentum. The title of this playlist is called The Beauty of Physical Argument. And we're circling back to a topic that we've seen before, where I'm trying to differentiate between something that we observe to be true in nature and something we assume as a postulate about how nature works. The two kind of different things. So let's go ahead and define what angular momentum is. I'm going to say that angular momentum, capital L, it's a vector quantity, first of all, but it's going to be equal to mr cross v. And if you're not familiar with what the cross product is, there's tons of videos, Khan Academy, whatever, out there, and there's content on the internet that you can sort of teach yourself that pretty easily. And what I'm going to tell you is that the magnitude of the angular momentum is constant. Okay, and getting back to the first thing I said, I can't prove this. All we can do is measure it and know that it's true. For this orbital system where a planet is orbiting around a sun, recall from the rules of cross products that this is going to be mvr sine theta. That's the magnitude. And somehow the speed, the radius, and the angle all sort of work together to make it constant. So that's the first thing we need to know. And the development that we're going to go from or work from is based on this fact. So basically, there's a lot of very clever mathematical tricks. There's a couple of vector identities here on the side that we're going to need. And yeah, it's basically a lot of very clever mathematical manipulation of this quantity L called angular momentum, which is a constant for this system. So let's go ahead and take L dot product with itself. And we know that this is magnitude of L squared. I'm just going to call it capital L squared, sort of drop some of the nomenclature or some of the symbols. So we can rewrite one of these, and we see that we can rewrite, say, the left one as mr cross v dot L. And take the mass outside. I'm going to take the mass outside. And this certainly still equals L squared. And we're going to use that second identity here. Let's call these 1 and 2. We're going to use 2 here now. And what we're going to convert this to is basically we have the right side, and we're going to convert it to the left side. So it's going to become m and then r dot v cross L. So what have we done? We haven't done anything really yet, but we've motivated ourselves to ask what is v cross L. The way we're going to do it is possibly even more convoluted. We're going to take the time derivative of v cross L, and there's sort of a product rule of differentiation that applies to cross products, is that you take the time derivative of v first, you get dv cross L, dv by dt cross L, sorry, and then you add v cross dl by dt. Now I told you that L was a constant. So what do you know about dl by dt? It's 0. So we know that we have this sort of identity, and also dv by dt in vector form is just the acceleration. Okay, so we're moving in a direction here. Let's now calculate A cross L. All right, and A cross L is really A cross, and I'm going to take the M outside again. It's something that I'm going to do frequently. And And what is L? It's going to have this R cross V term in here, R cross V. So now we need to use the first vector identity that I gave you. And we find that this is equal to the mass, and then it's going to be, let's use a big bracket here, it's A dot product with V times B, and then B is R, minus A dot product with R times the vector V. Okay, so this one definitely feels a little more complicated to deal with, and certainly it is. But let's recall what our inverse square law is. We derived it in the very first video in this series, and we said, let's say if you have mass capital M here, and then at some distance r, we have a smaller mass, little m. I told you that the acceleration would be negative g capital M over r squared. We derived that. Now, in terms of vector quantities, what we can do is we can define sort of a little r hat vector, that points in the direction of the radius. And as a convention, we're going to use that. So we're going to say that A is actually in the r hat direction. So that sort of sorts out the first one. So what about velocity and radius? Well, if we're going to use a polar coordinate system, we need to derive those quantities, okay, where we have a theta here and a radius. So a polar coordinate system basically puts the theta into the vectors, into the basis vectors, as opposed to the basis or the vector quantities or the vector components. So let's write down a couple things that we know so far just to kind of get started here. We know that r in normal notation is equal to r cos theta, r sine theta. Okay, in just normal plain Cartesian. If I then define r to be equal to the r is in the quantity times r hat, then implicitly what we've done here is we've defined r hat to be equal to cosine theta sine theta in vector format. Okay, so we can see something forming here. What we can do is we can take the time derivative of the vector r, and of course that's going to be v. Now this is a bit tricky, and I'm sure it would have tripped a lot of people up the first time that they had seen it or tried to do it. We have to remember that both r and r hat have quantities that either depend on r or theta. So you have to use the chain rule. So it's going to be, let's differentiate r, and you get r dot times r hat. And then the other piece is just going to be r times d by dt on r hat. So what is d by dt on r hat? D by dt on r hat is equal to d by dt on that vector, okay, cosine theta, sine theta. Complicating things further, in this system, this guy is rotating around the sun. Well, what do you know about theta? Theta is a function of time. We know that. So it's more chain rule, basically. The derivative of cosine gives you minus sine theta, and then theta dot, because that time derivative has to come out, and then sine theta becomes cosine theta times theta dot. And of course, we can take the sort of the theta dot is the magnitude outside of this vector quantity. All right, so we need to define one more quantity, and then I'm going to cut this video off. To get d by dt on r hat, we have to know what we mean. Well, I told you that this was r hat there. I'm going to tell you that in addition to r hat, let's do it in pink, there's another vector at a right angle. I guess it should be the same length. Oops, I'm erasing things. There's another vector at a right angle to r, and we call it theta hat. And I like to draw it really big, and I'll draw it really big just so we can get a really good good grasp on what theta hat is. So I put r here, and then theta hat is this way. So I can't seem to get these lines straight today. Okay, so I told you r was cosine theta, sine theta. Now we can ask the exact same things about the same questions about this. So this one was r hat, this vector here, and then this vector is theta hat. Let's call this theta hat. So in terms of the coordinates, the Cartesian coordinates, what's theta hat? Theta hat, you can reason it just by looking at it. The cosine of the theta gives you the y component. So to project this unit vector onto the y, you get cosine theta. And sine theta projects us on the x-axis, but we need a negative sine theta because it's we can see it's back this way. All right, so what we've noticed here is that this definition comes back in. So we actually get, just to finish this, we get d by dt r hat equals theta dot theta hat. Okay, so to complete the vector v, remember what we're doing here, we're solving this guy. The vector v is r dot r hat plus r times theta dot theta hat. Or you can write it as a column vector as r dot and then r theta dot. Okay, in the next video we are going to continue this and work out what that elliptical orbit is. So I'll catch you next time.